In last lecture, you studied types of solids, crystalline solids, which has two types, single crystals or monocrystalline solids, and polycrystalline solids, and then amorphous solids. Here we have to study the structure of crystalline solids, that is crystal structure. We are studying here crystal structure. And in order to understand the crystal structure, there are three basic concepts, namely space lattice, then atomic basis, and the third concept is unit cell. These are basic concepts of crystalline structures. In order to understand the crystal structure, you must have clear idea about these concepts, then only you will understand crystal structure. Let us study one by one. The first is space lattice. Space lattice is actually imaginary concept, but even though it is imaginary concept, it has definite relations with arrangement of atoms in the crystal. Okay, it has definite relation with atoms in the crystal. Or you can say that it is actually a framework on which actual crystal structure is based. Okay, it is a framework on which actual crystal structure is based. So first let us define the concept, definition of it. It is defined as infinite array of points in three dimensions. It is infinite array of points in three dimensions such that every point in it has identical surrounding or environment. So this is a condition. If you want to arrange the array of points, then you can arrange by n number of ways. But there is a condition, and the condition is that each and every point should have identical surroundings. Then only we can call it space lattice. So to understand it, let me draw the diagram for this. I am showing the points, that is the infinite array of points. Okay, this is infinite array of points. I am showing two-dimensional here. I can only show two-dimensional here. So here it is an infinite array of points in two dimensions. And we have to show that every point in it has identical surroundings. So this is array of points in two dimensions. Let us say this is vector A in x direction, and this is vector B in y direction. These vectors are called fundamental translational vectors. Vectors A and B. They are called fundamental translational vector because if you multiply these vectors in x and y direction, we get entire these two-dimensional points. Now this is space lattice only if each and every point has identical surroundings. To show that each and every point has identical surroundings, I am assuming here this translational vectors equals to 1. Let us assume that this A is equals to B is equals to 1 for simplicity. Then I will consider any 2 points in this diagram and show that both are having identical surroundings. For that, let us consider this point, name it as point A. Now to show that they have identical surroundings, I will start from that point and move towards x direction. I find another lattice point at distance 1. Then from that point I will move towards north direction. I find another lattice point at distance 1. Then I move towards the northeast direction and I find another lattice point at distance root 2. Then I will move towards north-northeast. I find another lattice point at distance root 5. So I can say that this is the surrounding of atom A in one quadrant. I don't have to show all the 4 quadrants. I am showing only in one quadrant the surroundings of atom A. Then I will consider another point. Let's say this is point B. And similarly here, when I move towards east, I find another lattice point at distance 1. And when I move towards north, I find another lattice point at distance 1. Then towards northeast direction, there is another lattice point at distance root 2. And then towards north-northeast direction, there is another lattice point at distance root 5. And this is the surroundings of point B in one quadrant. When you compare the surroundings of point A and surroundings of point B, it is clear that point A and point B both are having identical surroundings. Mathematically, you can say that. So, point A, points A and B are having identical surrounding. And similarly for all other points. So you can say that this whatever I have drawn is two-dimensional space lattice. Okay, this is two-dimensional space lattice because we showed mathematically that these points have identical surroundings. If the points have identical surroundings, then that points are called lattice points. Okay, these points are called lattice point, and that is the space lattice. Then I will go to the next important concept, which is atomic basis. As I said, space lattice is imaginary concept, or it is a framework on which actual crystal structure is based. Now we have to relate this space lattice with actual atomic position in the crystal structure. And to relate that, we have introduced here a concept of atomic basis. According to this concept, atomic basis is every lattice point is associated with one or more atoms. Okay, every lattice point in the space lattice is associated with either one atom or it can be associated with more than one atom. Then that is called atomic basis. In other words, basis is the assembly of atoms. This atomic basis is assembly of atoms. There can be one atom or there can be number of atoms. So it forms an assembly of atoms. And each basis, that is the number of atoms associated with every lattice point, should have identical composition. That is how many atoms are there, which atoms are there, whether there is a one carbon or two oxygen or whatever. So their composition should be identical at every lattice point. Then they are identical in arrangement. You know how they are arranged, which atom occupies which position. That is arrangement of atoms. And identical orientation. That is angle between these atoms. They, if this is the correct, then only you will get the actual crystal structure. So basis is nothing but it is an assembly of atoms which is identical in composition, identical in arrangement, and identical in orientation. So in other words, you can say this basis is nothing but a building block. This is nothing but building block. And when this building block represented with correct periodicity in three dimensions, we get actual crystal structure. This building block with correct periodicity in three dimensions gives actual crystal structure. So from imaginary concept to the actual crystal structure. Let me show the diagram for this. So first let me show the two-dimensional space lattice here. This is space lattice. Now, as per the definition of atomic basis, every lattice point in this case is associated with one atom or more atom. So, plus every lattice point is associated with one atom or more atom. For convenience, let me assume that every lattice point is associated with three atoms. Okay, so the composition is three atoms. There can be, one hydrogen, one carbon, or whatever. It is an assembly of three atoms. Their arrangement is shown here, which atom sits where. Their angle is also there. What is the angle between them? It's there. So this is nothing but a assembly of atoms, which we call atomic basis. Okay. So as per the definition, every lattice point here, in this case, every lattice point is associated with, as per our example, three atoms. These lattice points are imaginary concept. So instead of showing lattice point at that position, we have to show atomic basis. So it is nothing like you have a stamp of atomic basis and you should stamp every point with this atomic basis because these points are imaginary points. But that points are associated with atoms. In this case, three atoms with such an arrangement and orientation. So this gives, so there is a one trade atom at every position. Similarly, there is one slightly greenish atom at this position, and then there is other color atom at this position. So in this case, we have stamped every lattice point with the atomic basis with correct symmetry, correct composition, correct arrangement, and correct orientation. Then this gives us crystal structure, actual crystal structure. So we have related here imaginary concept to the real structure of the crystal. So that is the atomic basis. Now if there is one atom per lattice point, in this case, if there is one atom per lattice point, then it is called monoatomic crystals. If there are two atoms per lattice point, then it is called diatomic crystals. If there are three, then triatomic, etc., etc. We are going to study in this chapter structure of monoatomic crystals as well as structure of diatomic crystals. So that is the concept of atomic basis. Then let's go to another important concept, which is the unit cell. Unit cell. Unit cells are drawn in the space lattice. Generally, unit cells are drawn in the space lattice. So first let me insert a diagram of two-dimensional space lattice, which I have already shown over here. This is a two-dimensional space lattice, but here, ready-made diagram I will insert here. Let me reduce that in size. So this is two-dimensional space lattice. Okay, infinite array of points in two dimensions such that each and every point has identical surroundings. That is the definition of the space lattice. And these points are called lattice points. And in this space lattice, I will show you some of the unit cells. Basically, unit cells are nothing but it is the smallest block. You can define unit cell as smallest block. Instead of block, you can say geometrical figure. Smallest geometrical figure, or you can say smallest fundamental elementary pattern. Fundamental elementary pattern from which actual entire crystal structure is constructed. From this entire crystal structure is constructed. From which entire crystal structure is constructed by repetition in three dimension. Repetition in three dimension. In this case, I will show only two dimension. And this smallest geometrical figure has all the structural properties of solid. Okay. It has the smallest block or geometrical figure or fundamental elementary pattern that has all the structural properties of the solid. Then that smallest block is called the unit cell. Now in this diagram, I am showing some of the unit cells. You can choose it by different ways, but actually I will show all the different types of unit cells here. But actually every space lattice is having only one unit cell. For example here, see I can draw this unit cell. I will name this as A. So for me, this is the smallest block. And if I repeat this smallest block in these directions, I will get entire space lattice. But in actual crystal, every lattice point is associated with atoms, one or more atoms. So repetition of this unit cells gives you actual entire crystal structure. But in this case, since I am drawing in this space lattice, I am showing if I repeat this unit cell, this block in this direction, I will get entire space lattice. Another way, I can also select this way, unit cell like this. Let's say this is my unit cell B. You can see that repetition of this also gives you entire space lattice. This space lattice doesn't mean these many points only. There are infinite array of points in the two dimension in this case. Or I can select unit cell like this. This is my unit cell C. As you can see, repetition of this in two dimension gives us entire space lattice, two-dimensional space lattice. Then another way of selecting the unit cell is, I will select the unit cell this. This is my unit cell D, and I can also select unit cell like this. And this is unit cell E. As you can see in this diagram, I have shown two types of unit cells. This A, B, C is one type. A, B, and C unit cells. For these unit cells, you can clearly see that lattice points are located at the corners of the unit cell. Lattice points are located at corners of unit cell, and effective lattice point per unit cell. You can see there that every lattice point is shared with 4 unit cells here. See, I can draw one unit cell over here, another unit cell over here, another unit cell over. So this point is shared by 4 unit cells. And so its contribution to the particular unit cell is 1 by 4. And for unit cells say A, B, and C, there are 4 lattice points at the 4 corners. Each one is shared by 4. So its contribution to any unit cell is 1 by 4 into, there are 4 corners. So 1 by 4 into 4, that is equals to 1. And if this is the case, then that unit cells are called primitive unit cells. So A, B, C are primitive unit cells. In unit cell, if lattice points are located at the corner of the unit cell and effective lattice point per unit cell is 1, then that type of unit cells are called primitive unit cells. Then I will consider another unit cell D and E. This D and E unit cells, as you can see, where are the lattice points here? See the unit cell D. Lattice points are at corners of the unit cell as well as at the midpoint of these two edges. Similarly, if you see the E, lattice points are located at the corners as well as inside the unit cell. So, in case of D and E, lattice points are at corners and inside or on the edges. In 3 dimension, it is faces on the edges of unit cell. And second is effective lattice point per unit cell. Effective lattice points per unit cell. In this case, you can see there are 4 corners here. Each corner is shared by 4 unit cells, and so it is 1/4 for D. It is 1 by 4 into 4 plus there are 2 atoms or lattice points on the edges, this and this. And these two are shared by the 2 unit cell because one more I can draw over here and one more I can draw over here. So these points on the edges are shared by 2 unit cells. So its contribution is half. So half into, there are 2 lattice points on the edges. So half into 2. So that is equals to 2. In case of unit cell E, as you can see, there is one atom inside one lattice point inside the unit cell, which is not shared with any other unit cell. But these corners are shared with 4 unit cells. So for E, effective lattice point per unit cell is 1 by 4 into 4 plus 1, that is equals to 2. So if there are unit cells in which lattice points are located at the corners as well as inside or on the edges, and effective lattice points per unit cell are more than one, then that type of unit cell is called non-primitive unit cell. So broadly, there are two types of unit cells, primitive unit cells and non-primitive unit cells. So whatever I have shown here, I have shown unit cells in the space lattice as well as this is a two-dimensional space lattice. But actually, instead of lattice point, there are atoms, and instead of two-dimensional space lattice, there is actually three-dimensional space lattice. So I am showing here three-dimensional unit cell now separately. I am drawing three-dimensional unit cell. So this is three-dimensional unit cell. For three-dimensional unit cell, there are eight corners. And to understand it correctly, let us consider monoatomic crystals here. So when we say monoatomic crystals means every lattice point in the space lattice is associated with only one atom. So in this case, instead of this lattice point, now there are atoms but in the three dimension. So I am showing the atoms. So let's say there are eight corner atoms here. There are eight corner atoms. Now arbitrary arrangement of crystal axis is marked by X, Y, Z. This is the direction X, direction Y, and direction Z. Remember that this is very important. Direction, direction of this arbitrary axis X, Y, and Z. Always show this as a X, this as a Y, and towards the north direction it is Z. Do not ever change. If you take this as a X, this as a Y, and this as a Z, then I will give you 0 marks. So no, never change, interchange the direction of the axis. Always keep the same way. So arbitrary axes are marked by X, Y, Z. These are nothing but crystal axes. And there are vectors A, B, and C. This is vector A along the x direction, vector B along the y direction, and vector C along the z directions. And these vectors A, B, and C are independent. They are independent, non-coplanar vectors. Independent and non-coplanar vectors and called crystal or lattice axis. They are also called lattice axis or crystal axis. And these vectors A, B, and C are nothing but the intercepts along x, y, and z directions, and they determine the dimension of the unit cell. Okay, they define dimension of unit cell and called primitives. Okay, A, B, C. These three vectors, which are independent and non-coplanar, are called primitives. Then let me show you the angle between B and C is given by alpha. Angle between C and A is given by beta, and angle between A and B is given by gamma. So this alpha, beta, gamma, alpha is angle between B and C, beta is angle between C and A, and gamma is angle between A and B. These angles are called interfacial angles. So if you want to state the lattice parameters of the unit cell, lattice parameters of unit cell are primitives, that is vector A, B, and C, and interfacial angles. Okay, primitives and interfacial angles are lattice parameter of the unit cell. So in this lecture, I have explained you the three basic concepts: space lattice, atomic basis, and unit cell, which are very important